This is my Physics 2211 Lab 5 video on a falling slinky. The purpose of this lab was to measure the motion of the bottom of a slinky held in the air after dropping it from rest and compare it to a computer model that accounted for the tension from the top of the slinky, the drag, and the gravity. The main result of this lab was that the model deviated from what actually happened during the experiment, and it showed that the spring would not fall as far as it did in the same amount of time. The fundamentals in this lab include Newton's second law of motion, which is given by the net force equals mass times acceleration, where the net force was the force from gravity and the force from drag, or the force in gravity and the force from tension at the top of the spring. It also used the position and velocity update formula, which can be derived from Newton's second law of motion. We also used the gravitational force, which was negative mg in the y direction, drag, which is given by this formula here, and we calculated the equilibrium, since at the point where the top is first released, it will be at equilibrium and the bottom of the slinky will not be falling. Therefore, the tension will be equaling the force of gravity in the negative direction. The model of this experiment had the system being the slinky, while the surroundings was the earth and the air. The initial conditions was the position was near zero, the velocity was zero, and the experiment ran for a total of 0.843 seconds, and time was measured every 0.0033 seconds. This is a picture of the tracker video where the slinky started in the man's hands right here, and then he released it, and the bottom of the slinky was tracked as it fell to the ground, showing this graph of its Y position. This is the first part of the code, which include the initial conditions such as the mass of the slinky being 0.2 kilograms, the initial position vector, the change in time, gravity, and the drag constant, which was closest to the experimental model when it was set to zero. There was also the first calculation loop, which accounted for the fact that there was still tension from the top of the spring, as seen here, where the net force was the weight force plus the tension from the top of the spring, and it modeled the velocity and position changes over the change in time. Then in the next loop, we had the net force being just the weight force and the drag force, and then did the same thing with the velocity update and position update to measure it over time. Overall, the results showed this, where the experimental they both started off at zero for a while, and the experimental started to fall off much faster than the code model did. And overall, it showed that the code model would not fall as far as the experimental model actually did. The error in this lab includes the possibility that the position and tracker was not always accurate, since the quality of the video was not super high and it was hard to always accurately measure the bottom of the spring. Additionally, there was some sideways movement of the spring as it fell, which could have shifted some of the velocity it had and caused the bottom of the spring to not be where it would be expected to be. As well as it did not account for the fact that the velocity of the top of the spring, when it came into contact with the bottom of the spring, may have given it an extra force that slightly accelerated it. For the discussion question, the first one is going to be, why doesn't the bottom of the slinky move at first? And as mentioned before, the force of tension coming from the top of the slinky cancels out the weight and the gravitational force from the bottom of the slinky. This results in an equilibrium, which causes the bottom of the slinky to not move until the top of the slinky hits it and the spring force, or the tension force from the top, disappears. Then, what would happen if you modeled only the top part of the slinky? In this case, it would look just like any other falling object, since there is no tension force on it to slow it down, so the only thing affecting it is the force of gravity, and it would look like just any other model falling down. And that's all I had for this lab. Thank you.